Hello everyone. This presentation is about second part of the chapter on production of value-added products from biomass, even though the main topic was already discussed, and I hope you got the main message that many chemicals and fuels can be produced from biomass, but of course productions must be techno-economically and even environmentally viable. Especially, it has to be competitive with similar products from other industries, for example, from petrochemical industry. So this chapter is just to give you a bit more insights into some other products that can be produced from biomass. And I hope that this will help you to improve your insights into the world of value-added products from biomass. Okay, so let me minimize this screen. Okay, uh, this slide is about some uh, fiber-based products that you can produce from lignocellulosic biomass or just simply wood, for example, woody biomass. The solid wood itself, that it can be used as a construction material for making kitchen cabinets, but itself also can be used as a raw material for other products. If the solid wood can be made, can be pelletized, the pelletized of solid wood can be used as a biofuel, as you know. Uh, so it is about the wood. But you know that in pulp and paper industry, for example, we make wood pulp. From the wood pulp, also you can make several cellulosic products. For example, you can make biosensible papers, smart papers, nanocellulose crystalline material that we are going to discuss later in today. And we can produce composite products, for example, new packaging materials, or and even from the solubles of the pulp, we can make other products like viscose, rayon, cellophane, acetate, and some other products. Of course, viscose, rayon, and others. They are in interesting products. If you are interested to know those processes, you are encouraged to go and find out how the processes look like. Uh, and today, maybe some of them are going to be discussed today. So, in general, from uh, a biorefinery that works that takes raw materials as forestry residuals, you know that you can make a wide spectrum of uh, fuels and chemicals. So we already discussed that. Now let's a bit talk about some applications of ingredients of the woody biomass, for example. One of the most important ingredients of woody biomass, as you know, is lignin. As a reminder, woody biomass, uh, the three main parts are lignin, hemicellulose, and cellulose. Of course, there are some others, but these three are the most important ones. So you can produce lignin from woody biomass and then use that lignin to make in downstream some other products. So what are the sources for lignin? In other words, how you can produce lignin. So one of the sources of lignin is kraft lignin. Kraft lignin is rich in carbon, more than 60%, and it has less content of sulfur, and it can be obtained from residuals of black liquor by simply reduction of the pH. Another source of lignin is lignosulfonates, which is produced from sulfate processes. And in those processes, for example, um, solutions of sulfuric acid are used in the presence of some metallic cations, and so in order to dissolve parts of the lignin, part of the woody biomass, and eventually lignosulfonate is produced. One of the technologies is the technology by Tembec. So if you are interested, you can go and familiarize yourself how this works. But of course, lignin can be also supplied from hydrolysis process. So which is in fact subsequent extraction of lignin by a kind of organic solvent, for example, acetone and methanol, or by aqueous alkaline solution. Another source of lignin is lignin organosol, and another one is lignin soda. So as you see, all these processes really depend on the type of the solvent or agent that are used in order to extract the lignin from the woody biomass. So if you are really interested to know each of these processes, you can go to literature and find out how each process looks like, and how each agent or solvent impacts the quality and the efficiency or yield of lignin separation. But the physical chemical properties of lignin really depends on the type of biomass and the process of extraction. So even though, if you remember, most of the lignin contains phenolic groups, but lignin from one biomass to another could have some differences. Also, if you use, for example, solvent extraction, or if you use hydrolysis, acidic hydrolysis, for example, so you will have some impurities, definitely are not the same feedstock. But anyway, supposedly you have to do maybe some pretreatment, some purifications in order to remove some impurities. Still, there could be some differences in terms of physical chemical properties that uh, uh, you observe from the liquid that you have produced. So after you have lignin, lignin has a lot of applications, a lot of very interesting applications. When I say application, of course, one application of lignin could be as a source of energy, as a biofuel. So you can burn it or you can gasify it. But now our focus is on non-fuel applications of lignin, for example. So lignin is a source for composites that is a source for polyolefin composites. So you know that there is a huge market for polyolefins like polypropylene and polyethylene, and their demand is more than 100 million tons per year. So you can produce polyolefin-based composites from lignin, and the lignins that you produce from these polyolefin-based products from lignin can be in fact mixed with polyolefins that are produced, for example, from petrochemical industries, and in order to improve the carbon footprint of the synthetic material. So another application of lignin is to substitute phenol formaldehyde resins. So phenol formaldehyde resins are used as additives for the fabrication of wood panels, and usually lignins represent interesting properties that are usually, and for that reason, they are considered to even replace part of the phenol that is originated from petroleum. Another application of lignin is to make uh, carbon fibers. So these carbon fiber that are produced from lignin, usually they have very light density, so they are light, and they have a lot of applications in aerospace and car manufacturing applications. And since by using this carbon fiber, the weight of the final product is low, the energy consumption, for example, energy consumption of the cars or airplane is going to significantly less. So another application of lignin is to substitute carbon black. Carbon black is a material that is used as an additive into manufacture rubbers and specifically to manufacture, for example, tires of the vehicles. And this additive gives a special varying and abrasion resistance to rubbers, and also it gives a interesting or promising um, resistant tensile resistant to rubbers that are produced. So carbon uh, so substitution of uh, carbon black, uh, uh, carbon-based fibers, and phenol formaldehyde are three important applications of lignin as a substitute material, beside production of composites that are based on polyolefins. So, talking about phenol formaldehyde resins that we said uh, could be produced from lignin. So if you use, you know that in lignin you have phenol groups. So if you substitute the phenol by lignin by 25%, the consumption of formaldehyde in those resins will be down to will be decreased to 8.3%. And if you substitute uh, the phenol by lignin at a rate of 40%, the consumption of formaldehyde will be decreased to 14.5%. So by knowing that the cost of uh, phenol is $1,000 to $1,200 US per ton, and the price of formaldehyde is 500 to 700 US per ton. Okay, so if you do this kind of replacements, if you substitute part of the phenol by lignin, and also if you uh, uh, as a consequently reduce this formaldehyde, so you see that you can really produce something with a very high value. So uh, phenol formaldehydes, as already we said, are important compounds for making resins, and also derived from petroleum, and also for resins that contain isocyanates. But of course, uh, there are much more applications for phenol formaldehydes. For example, foundry resins, adhesives for making fiberglass isolations, binders used for stabilization of the soil during oil drilling, and also as binders used to make brakes of the cars. So, in general, uh, lignins are important. Uh, I can say uh, feedstock uh, uh, derived from biomass in order to make phenol formaldehyde resins that are really important uh, uh, products for industry. So another application of uh, lignin, as we discussed already, is to make uh, uh, carbon-based fibers. So these carbon-based fibers, usually they are produced from polyacrylonitrile or synthetic polymer materials, or from uh, tars from originated from the petroleum. But and they give, as I said before, they give interesting property to the final product in terms of weight. In other words, the weight of the final product is very light. So you know that these days we are all talking about reduction of greenhouse gases. So if your car, if any vehicle is lighter, has less weight, so less fuel has to be consumed in order to move it. So that's why these carbon-based fibers are very, very interesting products. On the other hand, there is issue. Production of carbon fibers from lignin is about $9.5 per pound, but uh, their production from, for example, polyacrylonitrile (PAN) is $5 per pound. Almost uh, these fibers from lignin are going to be twice more expensive. But as even you guys presented the last time in your presentations, we should not stop of thinking uh, uh, bio-based materials as a replacement, because our calculations show that they are the final product is going to be expensive. Of course, there must be more and more research and development activities, and of course we have to have a very strong and robust market evaluation, because at some point you may reach a production of, for example, carbon fibers from biomass, I mean from lignin, that is competitive to PAN. So just for your information, Boeing and Airbus, which are two large airplane manufacturers, so you know they are the most important users, I can say, of these carbon fibers, because airplanes are huge in terms of size, and it is very important to make sure that their weight is as low as possible. So uh, this table compares uh, current market of relatively, I can say, relative current market of carbon black, uh, PF resins, and carbon fiber. Okay, these are really, why I'm saying relative, because these data are extracted about 10 years ago, so the market could be a bit different. But the message is right still today. The message is that if, by considering this market, if 10% of this market belongs to uh, lignin, for example, so a large revenue can be generated just by uh, using lignin for these three products. But something that is interesting is that uh, almost 2% of the lignin has been valorized for value-added products, regardless of their use as a fuel, as an energy source. So there are a lot of, room in order to work on value-added products from lignin. And also, interestingly, usually lignin obtained from lignosulfonate is the principal source for making these three products. So of course, lignin has other applications. For example, in fine chemicals, one of these fine chemical is vanillin. Vanillin is the major constituent of vanilla extracts, and it has applications in agro-food and cosmetic industry as a flavor or aroma agents, and it can be used also as a kind of antioxidant agent, as a kind of anti-foaming agent, or even as a kind of a synthetic intermediate in pharmaceutical industry. And of course, in terms of production of vanillin, it can be produced from lignin sulfonate or by from craft carbon black liquor. Other application of lignin to make fine chemicals are dimethyl sulfoxide, and aldehydes. So dimethyl sulfoxide are used for the production of pharmaceuticals, and also they are constituents of cleaning formulations for microelectronics. They are also cryogenic They are also used as cryogenic preservation for the stem cells, thanks to a special property that this material give or provide in order to significantly lower the freezing temperature of water. Also, they can be used as solvent for producing polymers and some other applications. Aldehydes are used by oxidation of lignin. So by having aldehydes, you can make natural polyesters, and these natural polyesters, uh, in fact, can be used from syringal aldehydes or from other sources like vanille and para-hydroxy hydroxyaldehyde, parabenzene hydroxyaldehyde. As you may notice, I'm not chemist, so sometimes I have issue to pronounce correctly name of the chemicals. But what is important for the chapter is really to understand the potential of these products of biomass. Right now, we're talking about lignin, and also in terms of process, what kind of processes could be developed in order to make different products. So vanillin, as we said before, can be produced from black liquor. So as shown in this photo sheet, for example, after a spent liquor is obtained from pulp and paper plant, so you can apply oxidation to lignin, then you are going to end up with lignin and phenolates. Then you apply a membrane separation to separate the lignin and polymers from phenols. And by having the phenol separated, you can apply ion exchange process and then obtaining phenolic compounds. Then you apply crystallization and you produce vanillin and syringaldehyde. So this is just a rough flow sheet how to make vanillin from galactic. Now let's talk about another product that you can produce from biomass. If you remember, in a few weeks ago, we talked about biodiesel. We mentioned that at least there are three processes to make biodiesel. So conventionally, the biodiesel is used from oily biomass or oil seeds, for example, soya, sunflower, canola, and also from animal fats and um, used oils from restaurants. If you remember, uh, this during biodiesel, in order to have biodiesel production after the initial pretreatments on uh, biomass, you obtain a oil a oil product, and that oil product contains mostly glycerol, and this glycerol uh, is going to be mixed with the methanol and the catalyst, and then um, the mixture undergoes acidification and transesterification, and followed by purification, you end up with biodiesel. So, as shown in this diagram, for example, you see that uh, glycerin, glycerin is um, I can say, important is the important feed in order to make biodiesel, and the glycerin is the oil that you obtain from oily biomass or other sources of oil. So talking about glycerin, it has many applications beside biodiesel. Just I want to emphasize something. You have glycerol and glycerin. Glycerol and glycerin are essentially the same thing. So glycerin is mostly commercial name, uh, and it is usually a glycerol that contains also some impurities. So glycerol or glycerol is mostly the chemical compound itself, but when we say glycerin, it means that this chemical plus some other impurities. So what are in general, what are glycerols? Glycerol or glycerols in French are uh, a chemical compound that contains several OH groups. For example, as shown in this picture, this is the chemical compound that has three OH groups. This kind of glycerol that has three OH groups, we call it triglyceride. Triglyceride because it has three OH groups. So I'm not going to go to the chemistry because it is not chemistry is not the scope of this presentation. But what I want to draw your attention is that uh, glycerols have many applications. As you can see here, for example, you can do gasification and then do Fischer-Tropsch to make a biodiesel, or you can just do esterification and to make biodiesel from glycerol. But uh, if you take, for example, the byproduct of transesterification of glycerol, you can make glycerol carbonate that itself directly has applications, for example, to make to use as coating of polymers and other applications. But if you valorize this glycerol carbonate to other products, for example, glycidol and others, you end up with other products. For example, you can make some alcohols. Or if you look at this sales of products directly from triglyceride, I mean, regardless of biodiesel production and its byproduct, you can apply different uh, processes, including fermentation, including catalytic oxidation, including chlorination and others, in order to make different products as intermediates and then final products that have application. And these final products could be could have pharmaceutical application, could have drug delivery application, could have uh, food application, and many other purposes. So you can see that just by making, by extracting a glycerol from biomass, you have option to produce various products. Okay, so this gives you a kind of impression that uh, uh, what is really the potential of biomass derived products. So this is just an example of what happens in our body, but even in biological system, for example, in biochemical reactors, that if you have glucose, glucose in the presence of phosphate can undergo several transformations, and eventually it can be converted to uh, a mixture of glycerol and ethanol. So this is something that can happen even inside our body. And this NAD or NADH is a kind of enzyme that is used in the biological system to control these transformations. So talking about ethanol, that is a product that can be used, that can be produced beside glycerol. Now let's talk about ethanol. So ethanol is a very interesting product since centuries ago, as you know. And main producers of ethanol are US, Brazil, European Union, and China. You know that some countries have put a specific criteria in order to use ethanol even as a fuel. So, for example, in US, uh, up to 10% of the gasoline is mixed with is mixed with ethanol, for example. And I know that, for example, in some countries, if I'm not mistaken, Brazil, even some cars are the engine of some cars are designed in order to just drive by ethanol because they have a lot of sugar canes, for example, in Brazil, and production of ethanol is very promising. So uh, we don't want to discuss about ethanol. This is a very famous alcohol that not only as a fuel but also as a chemical has many applications. So from ethanol, uh, as I said, you can use it as a fuel or even you can gasify to make hydrogen. But you can also produce other products like acetaldehyde, ethylene, butadiene, and acid acetic. However, the note written here is very important. If you want to make other products from ethanol, you have to make sure that the process is economically promising. So you produce a product that is more expensive than ethanol. Otherwise, it doesn't make sense. Even though technically it is possible. For example, if you see here that, for example, the production cost of bioethanol is 250 itself, but the production of ethylene is $700 per ton, and production of acetic acid is $650 per ton. So, uh, you know, the production cost is high compared to production cost of bioethanol. So you have to make sure that for this high production cost of secondary products of ethanol is the process economic or not. So another alcohol that you can produce from biomass is butanol. So similar to ethanol that is usually produced through a biological system in a fermentation reactor, you can apply similar process but with a different enzyme, for example, different operating condition, and produce butanol. And butanol has also applications, for example, as a fuel or even as making chemicals. For example, by having butanol, you can produce uh, plasticizers, solvent, normal butyl acetate, glycol ethers, and acrylates, and some others. So again, you see that you produce one alcohol from a biomass, and that alcohol itself can be converted to some other downstream products. Another interesting product that you can produce from biomass with a high value, high added value is acid lactic, or in English, lactic acid. So again, by having a glucose fraction of biomass, we can apply fermentation and make lactic acid. There is one technical issue in lactic acid production, is it is because in order to neutralize this acid, they usually calcium lactate is used. But at the end, for 1 ton of lactic acid, you produce 1 ton of calcium sulfate. So there are technical issues in terms of waste disposal, for example, because this calcium sulfate has a kind of jelly, for example, property. So uh, its separation, for example, by filtration is not that easy. But anyway, regardless of the purification, having this um, equal mass of waste compared to lactic acid is something that you have to consider. But regardless of this technical issue, that anyway should be manageable at some point, you can produce again several products from by having lactic acid. And particularly, I'm very interested in high molecular weight polylactic acid, PLA, that you can produce. And this product is a biodegradable material that can be used to replace uh, plastic bags, to packaging, uh, food packaging materials, because it is biodegradable. It's a very interesting polymer that you can make. So that's really something interesting, because we know that plastics uh, are serious environmental issues when they are disposed, and so if you produce a biodegradable plastic, you're at a good condition. But of course, again, you can apply other processes like acidification, reduction, or dehydration, and produce other chemicals based on lactic acid. Another product that you can produce from biomass is succinic acid, or acid succinic. So also this acid has a lot of applications in downstream, and it is also a product that can be used by fermentation of biomass. So by having fermentation, we can make this acid. This table lists several types of acids that you can produce from biomass, and their applications are listed here. And this is really interesting. I want you to really go through the table and really familiarize yourself with different applications. Of course, you are not supposed to memorize them all, but as long as you get the picture of the importance of each acid for final applications, you get an idea of importance of biomass conversion to these products. So another product that we can produce from biomass, especially from the bleached biomass, for example, in this case, that bleached birch, craft pulp, you can produce xylene. Uh, Before we discussed about xylene and its importance, especially when we discussed the fact that um, this product can be also produced from petrochemical industry. But you can see that this product has a lot of applications, for example, in pulp and paper industry, in pharmaceutical, in chemical, food and fermentation industry. So again, a new uh, chemical compound from biomass for many applications. Another viewpoint uh, in terms of producing value-added products from biomass is uh, extractables from wood. So because these extractables that you obtain from wood, they have a special physical, chemical, and biological and therapeutic properties. They are interesting and they can be considered as value-added products. So, for example, two sources of these extractables can be considered. One is, for example, wood bark, in French, écorce, or nodes. For example, in the bark of the wood, uh, you can you can extract monomers of terpene, for example, pinene and limonene, because they have applications for uh, formulations of perfumes. You can extract tannins. These are agents that you can use to replace phenols of the resins, and also simple phenols that you can extract directly from bark. And they can be also used in order to make formulations of uh, food and health products for animals and even for humans. Some other extractables that you can make from the nodes are, for example, lignins that they have some biological properties. But something interesting that I want to now talk about, and it's really interesting to make from cellulosic part of biomass is nanocellulose crystalline, or NCC. NCC in French, but in English is called uh, uh, crystalline nanocellulose, or CNC. So NCC or CNC, sorry, uh, is a material that produced from cellulosic part of biomass, and it has a crystalline structure. So if you remember in the first sessions of the semester, we showed this picture. So in cellulose, you have some parts that are crystalline and some parts that are amorph. So by uh, grinding the wood parts, the for example woody biomass, and then applying hydrolysis, for example, under sulfuric acid, you can dissolve the amorph part of the cellulose and then extract the crystalline part in solid phase. And then these materials, they have a lot of applications. Usually, NCC material, I mean these nanocellulose crystalline materials, uh, they have dimensions about 120 nanometer in length and 5 nanometer in diameter. There is a company in Quebec that's called Celluforce. They have developed technologies to take advantage of these nanocellulose crystalline products. And I really want to encourage you to go and uh, search for the applications. But some of them are listed here. For example, these NCC or CNC materials can be used as biocomposites for the replacement of bone. You know that people, especially when they get old, they have bone problems. So they have to use synthetic material to replace that damaged kind of bone. So these nanocellulosic crystal material are one candidates. Also, they can be used for dental repairs. They have applications in pharmaceutical and drug delivery, and many more applications. I really want you to study by yourself to see how important they are. These are really interesting products that you can get from cellulosic part of biomass. So another chemical that you can produce from biomass is furfural. Already in previous session, we discussed about uh, processes for furfural production. So furfural can be produced from xylose, and by having furfural, you can end up with other productions. For example, you can produce tetrahydrofuran, you can produce esters or resins, you can produce nylon S, and some other products. Of course, uh, if you are interested on all these uh, processes, you are more than welcome, of course, to go and see, look at the literature and see how really uh, they can be produced. But what I want to emphasize again is that in this course, we are looking at biomass conversion as engineers. Okay, when we say engineers, it means that theoretically, from chemistry point of view, many products can be produced from biomass. But as an engineer, it is our job in order to make sure that from techno-economic and environmental point of view, even if, in terms of life cycle assessment, production of these products is viable. It is possible because maybe you produce something from a biomass which is extremely good. For example, it has, um, let's say you produce a special medicine that can, for example, cure a very difficult disease. If the production is very expensive, you have to make sure that it is possible to make it so you can make revenue. If you cannot make revenue, at least you have support of government or international agencies, since that's a very important medicine. For example, it's something that can kill coronavirus. So uh, always you have to consider any from chemistry point of view, many things can be produced from biomass and its derivatives. However, as an engineer, we have to make sure that all these products are can be produced from techno-economically uh, possible. So talking about furfural, so by having furfural, as we discussed, you can produce tetrahydrofuran. So currently, tetrahydrofuran or THF is produced from non-renewable resources, but it is a key component to produce certain elastic materials, and it is also a solvent for the synthesis of resins and also a co-solvent uh, for the printing ink and adhesives. Another product from for THF, by having THF, is PTMEG or polytetramethyl ethyl glycol. So in fact, this specific product is produced upon polymerization of THF, and it can be used for fabrication of spandex fibers or polyurethane resins. So these spandex fibers, what are they? For example, you know that for example, some sport wears, they have special tissues. They have a special elasticity, for example. So these kind of products can be used. You know why some sport shoes, for example, are very expensive? It is because the material that are used to manufacture those shoes so that they are elastic and they are and you feel comfortable when you wear them. So all those comfort that you obtain from those shoes is because of these chemicals that are inside the final product. So this is a kind of schematic flow sheet that shows how THF and um, uh, poly tetraethyl ethyl glycol can be produced. So if you have furfural under palladium catalyst, you can apply decarbonization, you make furan, and then under nickel catalyst and hydrogen, you make THF. But then THF can be polymerized at the presence of a special catalyst. Then the product goes into the methanolysis process where methanol is added with another catalyst. And then eventually you have neutralization, filtration, and purification finishing to get the final product. Here we talk about some catalysts. Even though it's not the scope of this course, just I want to share with you that usually catalysts in making any chemical are either heterogeneous catalysts or homogeneous catalysts. Then we say heterogeneous catalyst. It means that usually the catalyst is a solid powder, for example. So after you make the product, you can do, for example, filtration and recover the um, solid catalyst. So it can be recovered. But when you use a homogeneous catalyst, the problem is that homogeneous catalyst, it is always it can remain with the final product. You cannot separate it, and that's something that really adds cost to uh, expenses of the operation. So uh, so far we discussed about uh, some more products that can be produced from biomass. Okay, but now let's talk about kind of collaboration between a chemical industry and a forest industry. So as we discussed, right at the beginning of the chapter, if you want to produce a chemical from uh, biomass, you have to make sure that that biomass is competitive with the similar product that is produced from a chemical industry. So maybe one good way in order to uh, promote this pathway of biomass-based products is to have a kind of collaboration or integration with the chemical industry, and then they take advantage of one to another. For example, if you consider pulp and paper company or factory, of course they want to keep their jobs. They want to keep their personnel. So uh, if they collaborate with the chemical industry, so that uh, you know, for example, pulp and paper industry produces chemical A, and chemical industry also produces chemical A. But for example, they can blend uh, their products together and produce a new grade of the chemical A and then sell it together. So if pulp and paper industry collaborates with the chemical industry, since chemical industry maybe can produce with a cheaper price, by this kind of blending strategy, maybe a pulp and paper product can survive. And as a result, it can keep their jobs, and the pulp and paper industry can make additional revenues by producing byproducts, heat and electricity. And also, since the chemical industry is already well established and has access to market, final customers, so pulp and paper industry can also get that access. But on the other hand, even chemical industry will benefit from this collaboration. It's not only the pulp and paper that should beg the chemical industry. This collaboration is mutual. For example, the chemical industry can have access to bio-based raw materials in order to use for its own purposes. It can get shared infrastructure from for example, forestry industry, and the transportation cost can be decreased in production, even, and there could be less environmentally detrimental products by collaboration with forest industry, because as if you use biomass, so you are almost carbon neutral, and you take environmental benefits. So if you want to have this kind of integration or collaboration between a chemical industry and a biorefinery, okay, so there must be, for example, an optimal point in between, so that this kind of strategy can be viable from technical, economic, and environmental points of view. So again, this is an example for THF. THF can be produced from biomass, or it can be produced from a fossil resource. You can mix them together and then sell it. Okay, so uh, you know, for example, biorefinery process can sell THF directly to final customers. Even or a chemical industry can produce THF and produce it directly to final customers. But if they may mix together, if they blend together the products and if they collaborate together, they can take advantages, as we discussed in the previous slide. So this slide is uh, about some of the chemicals that are supported by Department of Energy, um, if they are produced from biomass, just for your information. But this slide is quite interesting and important, because as we discussed so far, many products can be for many chemicals and many fuels or biofuels can be produced from biomass. From biomass directly, like for example, woody biomass, as we discussed, or from ingredients of biomass, for example, from lignin or from cellulose, or even from hemicellulose, or from products that are produced from these uh, constituents of biomass, lignin, hemicellulose, and cellulose. So you can have, as we discussed before, you can have a large scheme of biorefinery scenario. But maybe your question is, okay, which product I should pick? Which product I should pick up? So it's a very interesting question. Uh, of course, it is really related to many parameters, even political parameters, not just technical and economic. Uh, but here, you have to make sure that certain criteria are possible. Are doable. Again, we are engineers, we are not chemists, even though maybe we have some chemists in our class, but I mean, the scope of this course is from an engineer point of view. An engineer is the person who wants to produce at a larger scale, so that it can sell to final products and then obtain a revenue. So uh, certainly, uh, uh, a product that you want to consider should be a product that is scalable, that you can scale it up. And it has to be techno-economy possible. In other words, you have to be able to produce at large volume, okay? And then you have to make sure that the product that you make or you are going to produce is going to be well established, so it can sustain. So it's not like a seasonal, and maybe it works for 2 years, and then after 2 years you have to close your factory. So yeah, it has to be sustainable. But as also we discussed so far several times, the product is better to be a product that can also substitute a product that is produced from petrochemical industry, because uh, it helps you to be less dependent on fossil fuel. So this was a kind of wrap up of production of value-added products from biomass. And if you are really interested, I really strongly suggest that you go to literature, go to patents, go to the website of the companies, go to articles, and to find out the details of these processes. Already, uh, we did a good job with you. We studied some processes that you presented last week, so you already understood that what kind of challenges are ahead of us in order to make value-added products that are commercializable and sustainable from biomass. I hope you could better understand the spectrum of value-added products that you can produce from biomass.